today's quiz we'll be looking at reaction coordinates and catalysis, and we're going to start with the following diagram. And the question asks to label the reactants, transition states, and products. And remember that when we have one of these reaction coordinate diagrams, what this shows us is the progression of a chemical reaction through its process, tracking its energy levels. And therefore, where we begin at the beginning of the reaction, so the first point in this extent of reaction, this is reactants, right? We start only with reactants. We proceed through a high energy state. We call this the transition state. This is the highest energy state along the reaction coordinate. You can think of this as a barrier that we need to give the chemical reactants enough energy to jump over or to be pushed over. And finally, we have the products over at the other side. And these are probably the three most fundamental points to recognize on a reaction coordinate diagram. A simple one like this, these are sort of the three relevant points, but there could be more, and recognizing these is really essential to understanding how chemical reactions progress. Okay, the second part wants us to do a calculation. So using this graph, we actually can calculate some more significant attributes of a chemical reaction, such as the energy change or the activation energy. Before we get to that, let's just take the numbers of these relevant states, right? So reading the graph, the reactants, let's say it's at 2 kilojoules, the transition state at 43 kilojoules, and the products at 15. If you got just very slightly different answers from this, that's just fine, right? Reading the graph, if maybe the energy of the reactants might be 1 kilojoule that you wrote, that would absolutely be fine, right? But they should be accurate according to the graph here. Now, the activation energy, like we just talked about, this is the energy to proceed over the transition state, so to get from the reactants to the transition state. So the question here is how much energy to get from where the reactants are at 2 kilojoules to the top of the transition state, which is 43 kilojoules. And the answer to this here, right, this is what is shown as the activation energy, and the amount of energy here is final minus initial, transition state minus the energy of the reactions, and that is positive 41 kilojoules. We have to give 41 kilojoules to these reactants in order for us to proceed, in order for us to reach the activation energy. The energy change, this is the change in energy from reactants to products, and so here we can show that on the graph as well. From the reactants to the products, we'll call this delta E, and this value is going to be 15 kilojoules per mole minus 2 kilojoules per mole, and that would be positive 13 kilojoules per mole. And now we've calculated these two values based on this reaction coordinate. Okay, next question is, what is a catalyst and how does it affect the activation energy of a chemical reaction? And this is kind of a textbook definition, but it is really important to understand what a catalyst does and what it doesn't when we're applying it to chemical reactions. So catalysts increase the rate of a reaction, and they're able to do this without, very importantly, don't change the reactants or the products, right? It has to still be the same chemical reaction, same reactants, same products. And they're not consumed themselves. Oftentimes they're used for the reaction and then regenerated, and as such we can often catalyze a reaction with only a drop of catalyst, as we're not actually consuming any of the catalyst molecules or sites upon which the catalysis is occurring. This is often done through making more stable transition states. Remember that the activation energy is the amount of energy to go from the reactants to the highest energy spot on the reaction coordinate. And if we can break a very unstable transition state into two more stable transition states, that's going to lower the energy of the activation energy, which will speed the reaction as it's easier to overcome that energy barrier. Okay, the last question is asking, is the reaction that we looked at in the reaction coordinate catalyzed or not? How can we tell if it's catalyzed? And when we look at this, to refresh our memory, here's that diagram. It appears to only have a single transition state. There's only one highest energy peak on this curve, and I suppose if you answer that, that's fine. Why or why not, though? It can be good to think about, well, what is an example of a catalyzed reaction? And it would be something like this, right? We could have a reaction with a single transition state that maybe is broken up into multiple transition states as we take one high energy point and maybe split it into multiple ones. And so, for example, this could be a reaction that has two transition states that may be catalyzed, right? This could just be a two-step reaction, but something where we are lowering the activation energy to make two transition states could appear like this, and this could be an example of a catalyzed reaction, whereas the original one that we're looking at does appear to be uncatalyzed.